Okay, the last talk today is by Jonathan Blum, and he will speak about border monopole.
Alright. It's loud? It's good. Yeah. Right. Well, thank you very much, the organizers, for having me. Come on. It's not my fault. I'm very excited to be in Budapest. My mom's side of the family is from about 3 hours away in Budapest, and so I feel like I'm slowly getting close to my ancestors. No, this is great. So thanks again. And yeah, I want to tell you about some joint work in progress with a bordered monopole foot here. So I'm lucky that this week one of the main themes has been bordered, and it's bordered Hagar Flare we've heard a lot about. And you've also heard something about monopole thermology yesterday from Stephen. So the idea here is, well, now that we know that gauge theory, which is what monopole flare theory comes from, and symplectic geometry, which is where Hagar flare theory comes from, they're deeply related, and in particular we have this beautiful theorem that monopole flare homology and Hagar flare homology are isomorphic. You can certainly ask, well, what is the bordered theory on the gauge theory side? And this is one approach to getting at that question. But you know, the history of looking for such a theory on the gauge theory side is a lot older than these recent results. So I'd like to say something about that first. Right, so when we talk about flare homology, usually what we think of is a functor, at least for three manifolds. We think of a functor from the cobordism category in 3 dimensions. So objects are closed or equal 3 manifolds, morphisms are cobordisms, to maybe Euclidean groups. So, you know, Hagar flare theory takes a 3 manifold feature group. But, you know, if instead of looking at just a 3 manifold, if you think about it, constructing these groups, it involves choosing some data, like complex structures or metrics, or depending on the theory. So we could also talk about a functor from, if you like, the cobordism category, enriched with extra analytic data, typically, maybe a Hagar diagram, it's a choice of data, to the category of chain complexes. So from this perspective, a 3 manifold plus some extra data gives you a chain complex, and cobordism between 3 manifolds plus some extra data gives you a chain map. From one chain complex to the other. And the sort of really you need to, in order to get a functor quotient by homotopy equivalence, in the sense that if we have a cobordism, which is a composition of W1 and W2, so this whole thing we'll call W, then what's true is that if you take the chain map for W2, compose it with the chain map for W1, that is homotopy equivalent to the chain map associated to W. Okay, so now we're looking at the level of complexes, but we need more data in order to define things. The reason you get the functor at the top is because this choice of extra data turns out, well, choosing different choices, there turn out to be canonical isomorphisms between the homologies of the chain complex you get. from different sources of data. And so by identifying these all together with these canonical isomorphisms, that's how you end up getting a group that doesn't depend on the data in the end. And I think Andras is going to talk about that somewhat. Right, Hagar Fleur side, for the monopole Fleur side, for example, you should look at primary numbers. Both. That's the width, not the length. So, all right, well, ideas going, as I understand it, ideas going back to people like Donaldson and Kaya, picture that there should actually be more structure here, coming from the geometry. And these ideas are difficult to implement rigorously at the time, mainly because of reducibles showing up in a lot of these theories. But the big picture is this, that we'd really like to go one level down. And so that means to a surface plus some data. Well, now instead of a functor, we're going to have something like a two-functor. So we want to associate to a surface a category. Except, that doesn't quite work. What you really need is an A-infinity category. And I'm going to talk about A-infinity language a little bit in a little bit. So there should be some A-infinity category, C of sigma. Now, to a three-manifold, which is a cobordism from one surface to another, we should get an A-infinity functor between these categories. And you can go one step further to a four-manifold with corners, in a sense. So here's a W, which is a cobordism of cobordisms. So sigma is down here. And you have four-dimensional cobordism with corners like this. This should be some A-infinity natural transformation. In other words, what's going on here should be, you should be able to cut it down one dimension. So it's something like 2 plus 1 plus 1. And what is this category that form associated with the surface? Well, in the case of gauge theory, the idea that is that, well, an object of this category, say the objects of this category are the set of ordered three-manifolds. So that's a three-manifold Y with boundary, together with a parameterization of the boundary, just like in Roberts-Cox. So the objects are all these three-manifolds with parameterized boundary C. The morphisms from one object, Y1, to another object, Y2, in this category, should be the Fleur complex from up there associated to the three-manifold you get by gluing Y1 to Y2, which you can do because both the boundaries are parameterized. Yeah, minus y2. Thank you. Yes. All right. Now, and the idea from there is that there should really be an infinity category that means that there's some multiplication maps given a sequence of morphisms produces another morphism. And again, I'll come back to that later. Now, this may seem maybe foreign to some, but if you're more on the symplectic geometry side, you should keep the sort of translated picture in mind. Namely, you should think instead of sigma, you should think, so here's sort of gauge theory, and here's symplectic. So you should replace sigma with sim-g sigma, a symplectic manifold. And there is an infinity category associated to a symplectic manifold like this called the Kaya category. So that is the symplectic analog is the HUN-REN category. And in particular, what a three-manifold with boundary is giving you, so here's Y with parameterized boundary. Well, in the case that it's a handle body, so it's called H, a handle body with parameterized boundary, what's that? Well, that's like a Hagar diagram with one set of curves. That set of curves gives you a Lagrangian, a torus, in sim G sigma. So in other words, the handle body is sent to a Lagrangian. And now what are these morphism spaces? Well, if you have a pair of handle bodies, that is a Hagar diagram, right? So if I have a pair of handle bodies on the left side, I'm going to get some, say, monopole or instantaneous working monopole for a moment. So monopole thermology, some gauge theory defined group associated to the three-manifold you get by gluing the two handle bodies together. So this is going to give us, say, monopole thermology on the gauge theory side. That's what this morphism space is. On the symplectic side, well, I'll get these two Lagrangians in the symmetric product. And the morphism space that you should think of there is the Lagrangian intersection Floer homology. So maybe I'll say Cm over here. Here we have Cf of L1 and L2, which essentially, which is exactly, the Hagar Floer homology. So given two parameterized handle bodies, we can get two Lagrangians over here, and then Hagar Floer homology is defined essentially as the Lagrangian intersection Floer homology. Now, this is not me being rigorous saying, well, therefore this group equals this group. This is just sort of the philosophy that I've been told. We know that there is all this infinity structure over here in this mechanic category, and so today I'm going to tell you what it should be over here on the gauge theory side, and develop a ordered theory, tell you what to associate with the surface that'll be very analogous to, well, it has a lot of parallels to some things that are on the Hagar Floer side. So the obvious thing we've heard about this week is ordered Hagar Floer homology. So I should say that, there is ordered Hagar Floer by Richards, Ozop, and Thurston. But what John and I are doing is actually more parallel to work of Healy and Tim Kurtz, Donkey and Tim, on the Hagar Floer side. They associate to the surface as a chi category and then develop a ordered Hagar Floer theory based on that approach. And of course, their work owes a lot to the so-called quilted Floer homology, which on the symplectic side is essentially just trying to make a two-functor instead of a functor in this context. Okay, anyway, so these are some ideas that have made a lot of progress on the holomorphic curves and symplectic geometries. All right. So, yeah, so what are we doing? So the sort of our project goals, and we've made a lot of progress, are following: to rigorously define this two-functor, so these structures. For monopole Floer homology. And again, the biggest problem there is the problem they had originally, which is reducibles make it difficult. And the other goal, the other thing we're doing that's maybe a little different than what's happened over here is our setup actually is most easy to define for the most powerful version of the theory. Not the hat version that you see in Hagar Floer, but the analog of CF minus or HF minus. So essentially, make sense of this for all versions of monopole thermology. But for those in the know, we should think of CF_, which is analogous to HM_, which is analogous to HF- by a horrible coincidence. The horrible version of monopole has a hat on top. But anyway, it's called HM_. And then the third thing, and this might maybe is the most interesting aspect, is that the category we're going to define, instead of using all order 3 manifolds, our category is going to have a finite number of objects. In a sense, what we're doing is showing that there's a subcategory which generates this category in sort of the growth and peak sense through surgery triangles. So that you don't need so many objects. And when you have a finite number of objects, instead of working with the category, you can sum up all your morphism spaces and call it an algebra. And so that's actually what we're going to do. So I'll explain that better in a moment, but let's say finite number of objects. And I should say that at this stage, we can certainly define what the two-functor does we can define it in the sense of what all these things are, given the surface of the data and 3-manifold and cohorts and quarters, we can define what they should be set to. Of course, then we want to prove that it satisfies all the axioms of the two-functor. We haven't finished doing that, but the first thing you want to see is the pairing theorem holds. That's sort of the basic axiom. And so that is something we can prove. And let me say that.
So you find too many options? I don't understand this.
So instead of looking at our objects being all 3 manifolds, ordered 3 manifolds with boundary sigma G, it will be a finite collection of parameterized handle lines. Will be our objects. Why is that enough is a topological theorem that I will get. But essentially, you need to show that any ordered 3 manifold can be expanded into a surgery hypercube of these parameterized handle bodies connect some S1 process views.
So the functor is defined on level to specify
You could, I mean, the functor could be defined on everything, but we don't need to. And we only want this finite set, and the implication is that all you need is this, perhaps even on the, so what's something that I think is not known on this Hager first side of Franke and Twing's work is, how many Lagrangians do you need to generate the Fukaya category of sigma sigma? In the genus 2 case, they show those 2 Lagrangians suffice, but in a sense, we're giving a finite set for any genus on the gauge theory side, and maybe a conjectural set on the other side, but it's not a very strong conjecture. Okay, so right. Okay, so what is this pairing theorem? So the pairing theorem says that the module we associate to. So remember, if we have parameterized, if we have object y1, this gets sent to some. No, before I state that, I should back up. Because there are finitely many objects, I'm going to rephrase what I'm doing as following. To a surface, we will associate not a category, but an infinity algebra, called an A. To a 3-manifold with parameterized boundary, we're going to associate an A infinity module over this algebra, call it C of y. And, well, if you like, to a cobordism of cobordisms, we're going to associate a map of A infinity modules. If you like, you can call it M of W. Now, this is a rephrasing because we have finitely many objects in our category, sum over all the markers of spaces. But, right. So I could be a little more specific now. Like I said, to construct these, what we do is we define for each genus G, okay, we have a finite set of H sub alpha of parameterized envelopes. And so the structure of our algebra it will be a direct sum over all pairs of these envelopes of the Floer complex we did by gluing one together. That's the underlying vector space. And the module we'll associate to Y is the sum over all alpha of the ways of gluing H alpha to the boundary of Y. So these are the underlying vector spaces of our algebra and module. The C on the right denotes Floer homology of the Floer complex of the closed manifold in all cases. On the left, it's our new notation. This is a manifold boundary. This is the surface. Okay, and now I can state, and now I haven't told you what the A-infinity structure is underlying all this, I'll come to that, but here's the parent theorem. Alright, suppose, well, I guess the easiest, perhaps, way to, right, suppose we have Y1 with outgoing boundary sigma, and we have Y2 with incoming boundary sigma. Okay? I should say that when you have outgoing boundary, you get a right module, and when you have incoming boundary, you get a left module. And the pairing theorem says that the module of Y1 tensor the module of Y2 in the A-infinity sense. These are two A-infinity algebras over in modules over A-infinity algebra is quasi-isomorphic to the complex of gluing Y1 to Y2. So this should look like what you saw in ordered Hagar for homology. You have a free manifold obtained by gluing two sides together. You can see that its Floer complex as some A-infinity tensor product of A-infinity modules associated to the two sides. For torus boundary, 2. And for genus 2, it's 5. And then it starts getting big fast. Let me point out one application of this. In the case of genus 0, our algebra associated with the two-sphere is essentially the formal algebra at the joint U, which you should recognize as the Floer complex of, this is the Floer homology of the three-sphere. Okay. You think of H minus 1. You can see easily this is the underlying vector space if I tell you that in the genus 0 case, our handle body is a ball, and there's only one parameterized boundary of a ball. So what do we do from our algebra? We take the two-sphere, we fill in a ball on both sides. That's the only thing we can do. That gives us the three-sphere. then we take its Floer complex. And if you choose your data right, you can make no differential in the case of the free sphere. And so this is the underlying vector space of our algebra. And this is, it turns out, an intrinsically formal algebra in the sense that there can't be any interesting infinity structures on it. So we get a pretty simple algebra. And now what the pairing theorem says in this case is that C of y1, how should I say it? So let y1 be some be what you get by, suppose you have z1 and z2, and that yi is what you get by removing the ball from zi. Okay? Z is some closed free manifold. Okay, so, sorry. Suppose z1 and z2 are closed free manifolds. Well, for this pairing theorem, we're supposed to look at manifolds with boundary, and in the zero case, they have boundary the two-sphere. So let yi be what you get by removing the ball from them. Well, then the left-hand side, what is it? Well, we're supposed to take yi and plug it out in all possible ways. But again, the only thing you'd be doing in the zero case is put the ball back. So the left side is just z gives you just this is the left side. The module associated to yi is just the complex of zi, but there is some infinity structure over our algebra, which is at the joint unit. The right side is what you get by gluing y1 and y2 together, but that's just infinite sum. So in other words, once the structure has been set up, the HUN-REN theorem of Floer homology of the connect sum falls out as the statement that the Floer homology of the connect sum is the A-infinity tensor product of these sort of Floer complexes of the two sides over the algebra of joint U. And if you like, you can think of this as essentially as the tensor product over f of joint U. That is, these Floer complexes have a module structure, the action of this endomorphism U, and you can take them, that means that they are modules over f of joint U, and you can take a tensor over f of joint U and get some module. It's almost like, it's like a derived version of tensoring over f of joint U. More rigorously, there's another version of this theorem in joint work with Rufka and Oswald, which comes to essentially the same conclusion, except it's phrased not in terms of the A-infinity tensor product, but in terms of the mapping cone. So you take the Floer complexes of these guys, and you look at the map between them, which is U tensor 1 minus 1 tensor U. So take this whole complex, and this is quasi-isomorphic to the Floer complex of the connect sum. So if you think about what this mapping cone is, the co-kernel is exactly the tensor product, not over f, but over f of joint U. Because what you're quotienting by is, the action of moving U from the left to the right. You can move U across the tensor product. There could also be some kernel, it turns out, in the gauge theory side, and that's why it's a more fancy tensor product. Okay. So we've heard a lot about A-infinity algebras and type A structures, type B structures this week, but I thought I would slow down to give a definition of A-infinity algebra, A-infinity module, and A-infinity tensor product. Because I thought that most of what I'm saying is just words and maybe it's not. I don't know. It took me a while to understand these things. I still don't understand them very well. So let me tell you what these structures are, so that I can then tell you how John and I can define how we define these modules. So what is an A-infinity algebra? Okay. Well, I'm going to work over the field of two elements to avoid signs, and all of this work actually is doing that, working over D mod 2 or F2 to avoid signs. So it's an F vector space equipped with a sequence of multiplication maps denoted by ui. And ui goes from A tensor I times back to A. And this is for all I greater than or equal to 0. And these have to satisfy the so-called A-infinity relations. And I do believe in drawing the pictures of the trees that you've seen. So I'm going to do that again, but maybe in my own way. So we think of these operators as having some number of inputs and an output. So mu I we represent by a tree where there are I inputs and one output. And I'll tell you what the infinity relations are. So there is one relation for each I. Okay? The first relation says that if you do mu1 and then do mu1 again, the result is 0. So when I write this, what I mean is mu1 composed with mu1 equals 0. That's mu1 and then mu1 again. So in other words, mu1 is a differential. All right, the second relation looks like this. So here, if you wanted to translate this into symbols, this would say that if you apply mu2 to mu1 in the first position, or mu2 to mu1 in the second position, or apply mu1 to the result of mu2, but the sum is 0. Okay? And what that translates to is the fact that mu2 from A tensor A to A is a chain map. In other words, it descends to give you a product on homology. Okay? Because the differential on the tensor of A and A is you apply differential in the first place, or you apply it in the second place. So this part represents the differential on the left, this part represents the differential on the right. Okay, so we have some product structure on homology, and coming from the chain level, you could ask, is it associated? And that's what the M3 is telling you. That this product mu2 is associated, but only up to homotopy, and mu3 is the homotopy. So for this, I'll just write down the relation. So, and then I'll tell you where I'm getting all these terms from. So the next relation involves 6 terms. This is a mu2 composed with a mu2. So is this. This is mu1 with mu3 and the others and so on. But the way you should group it is, here you have, if you like, A times B, so mu2 of A and B, and then you take the result and you multiply that by C. Here you have, first, B and C multiplied, and then you take the result and you multiply that by A. And here, these three terms, you can think of as the differential on A tensor A, composed with the M3. And this term is M3 composed with the differential on A. In other words, these two ways of associating this triple product from A tensor A to A are not necessarily the same, but they are on topic, and the homotopy is exactly the M3 map. And so on. So you have infinitely many of these, one for each I, and the way you write down the relation at each stage is you write down every tree, every composition of two trees, which has the property that if you glue it back together, you get, basically which has the property that you have the right number of inputs. That's all. So this is all ways to put two trees together such that the result has one input. Here's all ways to put two trees together so that there's two inputs, three inputs, and so on. That's all it is. So now you can write down all the infinity relations by a public table. Alright, so the philosophy is basically that if you want to stay on the chain level, then you aren't going to see an associative multiplication, but you will see associativity of the homotopy, and then you'll have, and then there's some relation of this associator and so on, so it's some kind of coherent system of higher and higher and higher homotopies, telling you how associativity behaves on the chain level. Alright, are there any questions about that? So that's what an infinity algebra is. And an infinity module is almost the same thing. So for an infinity module, M over A, it's again a vector space with multiplications. Now I call them Mi instead of Ui. They go from M tensor I minus 1 copies of A back to M for I greater than 1. Maybe I should. So I want M1 to be a map from M to M. Yeah, that's good. And they have to satisfy similar relations. In fact, they're the same relations. You just need another color of chalk. So, what are the relations? So you take another color of chalk and you draw your trees a little less symmetrically. And you saw Peter drawing these. Peter is often also called Robert. Maybe I need a really color of chalk. So the red is where your module element goes in, then you have some algebra elements, and when you get out, it's a module element. No? The relations are exactly the same relations. In particular, M1 is a differential. You might draw your relation for M2 a little differently. You can draw it like so. Okay, so here's it. But if you stare at it, oh no, I already got to the M3. You can apply the red there, the mu1 there, or the m1 there. I'll draw the first first two terms of the next guy, you can do this and this, or you can do this and this. These are the first two terms of 6, and so on. They correspond exactly to the terms up above. So you have a differential on the module, you have a chain map that tells you how to multiply an algebra element against a module element. That multiplication is associated with the homotopy. So MA times B looks a lot like M acted on by B. And so on. Okay, and then of course there's a notion of maps of the infinity modules, but that's getting too far afield. By the way, I can tell you what the infinity tensor product is. So if we have modules M and N, the A infinity tensor product, what you do is you take M tensor N. This looks like a bar resolution. So you have this direct sum of all of these vector spaces. Now, you're taking the tensor product of the left module and the right module. These are infinity modules. What you expect to get is just a chain complex, because you the actions are sucked in to the middle. And so I have to tell you what the differential is on this vector space. And the way it's defined is you basically draw every possible tree you can on this picture. In other words, this is one component of the differential. If you like, I could call this red and this white. So here's an M1. On the other side, you have a map like this as well. Now, if we go up to the next level, we could, for example, multiply an element here against one here, or we can multiply two algebra elements together, or we can multiply this algebra element against this guy, against the module element. But you also have a map that takes, for example, M and two algebra elements. I'll draw over here. M tensor A, down to M. So, looking like so. That should also appear. So, in other words, you just draw every possible map you have on this vector space, and the fact that that's a differential follows from the relations for these modules and the algebra. All right, so no, it keeps going forever. That's a dot. And you have 3 A's, and you have 4 A's, and you have 5 A's. You go forever. Yeah, it's an infinite sum. Yeah. But one nice property this tensor product has that the usual tensor product doesn't have is that if you have, say, a homotopy equivalence of modules, then you get a homotopy tensor with something, then the results are homotopy equivalent, for example. That's a property that the usual tensor product doesn't have, which is sometimes why people move to the derived tensor product, which looks a lot like this. Quasi-isomorphic. Yes. Okay. All right. So that's putting the pairing theorem in context, but of course I have to actually construct an infinity structure now using gauge theory. So that's what I'll do. Okay. So let's construct the infinity algebra associated to a surface. Remember, I have this collection of handle bodies, and the underlying vector space is, I'll just call it, the underlying vector space is the sum over all alpha beta of the Floer complex of H alpha glued to minus H beta. this map here was from here all the way to here directly.
It can jump.
Yeah, yeah. So the higher multiplications take you. Yeah. Right. So the differential is a sum of terms, one for each way of putting in a multiplication. And everything else is, maybe I should say it like this, and the point is here you just equate it. Does that make more sense? Okay.
And what would be U2? So the differential is the sum of
All of these.
and
All
that
of
would
these.
be the new one, right?
No, there's no. What I'm getting is just a chain complex.
N1, right?
What you get, this would be an M3, tensor be an going from here to here. It's an example of a term in the differential.
That would be a term in N3 in the tensor product.
No, the tensor product is just a chain complex. It's no longer, if you take the left module and the right module, you tensor them, you don't get a module. Yeah. Okay, so here's my vector space. So far, so good. Now, the mu1 is the Fourier differential. It's the unease summit.
So now the C means CDF.
This means monopole Fourier complex, and technically, what I have to do to define this algebra in the first place is, for every sequence of subscripts, I have to choose metric and perturbation data, and I have to do it in a consistent way. Assume that's all been done.
You didn't tell us what the sequence is.
What?
You said that there are some.
Yes, I haven't told you what these analyses are, but I can tell you more about that. Cool. But I'll tell you in the first cases, in the genus 0 case, we just have the wall. In the genus 1 case, you can think of the solid torus with, if you like, the sort of 0 and infinity parameterizations. In the genus 2 case, there's going to be 5 terms, and one way to think of where they come from is given to us by one. The 5 handle bodies arise as branch covers of 5 crossless matchings on 6 points. Given a crossless matching on 6 points, you can think of this as happening inside the ball, where the points are on the boundary of the ball, the arcs are inside the ball. If you branch cover a ball over some arcs, 3 arcs, you get a genus 2 handle body. And different matchings you can think of as corresponding to different parameterizations. These will be our 5. When you go beyond genus 3, these crossless matchings give us some, a catalog number's worth of handle bodies, but you need more to generate the category because the mapping class group of a higher genus surface involves curves that don't sit on, that are not preserved, if you like, by the evolution. They involve these other vertical curves. So then it's hard to describe what they are, but I can tell you that. Okay. Now, the mu2. So let's define mu2. So what is that supposed to be? Well, a component of mu2 should be a map from, so let's say I have mu2, I can look at the alpha beta component, or alpha beta gamma component of mu2. That should be a map from the complex associated to H alpha union minus H beta, tensor the complex associated to H beta union minus H gamma, to the complex associated to H alpha union minus H gamma. Mu2 really is a sum over all triples alpha beta gamma, but here's a piece of it. Okay? So I need a way to multiply a vector in here, an element here, an element here, and an element there. So to do that, we need a 4 manifold. And what 4 manifold do we make? Well, if you study Hegel terminology, you're working with these 4 manifolds. Robert, you want me to go this way or this way?
Clockwise.
Clockwise?
Yeah, sorry.
Okay, so I think this is the format. You may argue it's drawing on the top. Okay, so what is it? We have the surface sigma. We cross it with a polygon. A triangle, essentially. But I've drawn it as a hexagon. So it's a hexagon. But think of it as a triangle if you like, from the Hagar flow pictures. And now I have these boundary components, which look like surface cross interval. I can glue on handle body cross interval. So each of these represents a copy of the handle body H alpha glued to sigma. So here's handle body cross interval, here's H beta glued on, here's H gamma. In all cases, we're just gluing on a handle body cross an interval, but the way we glue them on comes from the different parameterizations, alpha, beta, gamma. This form manifold has three boundary components, which we should think of as incoming in these places and outgoing in this place. So what is this boundary component? Well, we have H alpha glued along sigma to minus H beta. Here we have H beta glued along sigma to minus H gamma, and here we have H alpha glued to minus H gamma. So this is a four manifold with two incoming ends, which coincide with these three manifolds, and an outgoing end, which coincides with that three manifold. And I claim, given such a four manifold and a whole bunch of analytic data, you get a chain map of that type. Now, to actually write down this chain map, it turns out it's not so simple as count monopoles on this coordism that limit from a generator here and here to one over here. The reason is because of reducibles. So the actual chain map ends up, you have to define it just like they always, in all the versions of monopole, you see these complicated looking formulas for the differential and for the chain maps and so on. They involve all kinds of broken trajectories as well. Same thing goes on here in the combinatorics. Looks horrible, but everything works, it turns out. And there's a nice way to organize it using path algebras, hypergraph, which I can tell someone about later. Anyway, so you do get a chain map out of this, and that chain map is going to define mu2. All right, now I have not too much time left. This doesn't look like an infinity thing yet. This just looks like I have a multiplication. What are the higher multiplications? So let's look at what a component of mu3 would be. So now I need a quadruple. This is going to involve a four manifold with three incoming ends and one outgoing end. So let me draw the four manifold. Here's alpha, beta, gamma, delta. Okay? So here I have H alpha union minus H beta. Here I have H beta union minus H gamma. H gamma union minus H delta. And H alpha union minus H delta. These are my incoming ends. This is my outgoing end. And I want to use this to define an M3. The problem is, so it's true that actually I can, from this, get a chain map. And this chain map will go from the complex of H alpha union minus H beta, and so the complex of H beta H gamma, and so the complex of H gamma H delta to the complex of H alpha. But this chain map will not be M3. It will not satisfy the relationship you want it to satisfy with respect to the lower multiplications. What it really should be is a homotopy. So it ought to have a different gradient shift, sort of up one. And where this comes from is that we're going to not count the monopoles on this coordism with just looking at just a single metric, but instead we're going to look at a one-dimensional family of metrics. And as for each metric in this family, is there a monopole? And if generically there isn't, but it's some finite number of metrics along the way, and one pops up, this will give us some non-trivial contribution to this mu3. So what is the family of metrics? What we want to think of is take these minimal chords across the polygon. Okay? Now, what three manifolds do these represent? This one represents H alpha glued to H gamma. This one represents H beta glued to H delta. Right? So these are the other ways you can glue, the sort of non-consecutive ones. And what we want to do is take a family of metrics which parameterize around an interval that starts at this picture in the middle, but as you move to the right, it'll, on one of these, start stretching normal to the three manifold, the hypersurface. It'll start stretching the net, stretching, 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 until when you get to infinity, you've cut, you stretch all the way. So what does the cut picture look like? Well, if I cut, then I have to break this into two pieces, like so. And then on the other side, I will cut the other way. I claim these two pictures correspond, if you like, to these two pictures in the relation that the M3 is supposed to satisfy. In other words, when you cut here, you see two triangles like we have here. In other words, this is a composition of M2s, of multiplications. In this picture, you're taking out A and B and multiplying them, and then taking C and multiplying that in to get some result. In this side, well, I didn't order my A, B, and C correctly. But in any case, if I put them in the right order, let's see. So I put A here and C here. Okay, so here we take B and C, multiply them together, then multiply A in. Here we take first A and B, multiply them together, and then multiply the result by C. So this M3 is defined by this four manifold with a one-dimensional family of metrics parameterized by the interval that when you move one direction, cuts it one way, when you move the other direction, cuts it the other way. And what you get out of that fact is that it satisfies this relation. That's to say, the M3 is a null homotopy. The operator associated to the interval metrics is a null homotopy for the operator associated to the ends of the interval, which are exactly the two ways of multiplying. And so on. So what happens when you have a new form, you find and so on, you get polygons with more sides, you get more chords, and now you're going to be stretching not just in one place, but in many places at the same time, in all ways you basically can. What this ends up looking like is ways of, on a polygon, triangulating, how to cut it into triangles. And those triangulations correspond to vertices of a polytope called the associahedron. The family of metrics that you develop for these higher views are going to be parameterized by higher dimensional associahedron. Interval, pentagon, three-dimensional associahedron, and so on. Each one dimension higher than the last. And put all together, they give you the same infinity structure. The only thing that changes when you want to find the A infinity module is you replace, associated to Y, is you replace one of these alpha, beta, gamma, or whatever, with Y instead. Now you see a module element, because you have Y with alpha, then some algebra elements, and then out comes another module element, Y with delta, with gamma, for example. So that's where the same idea is what gives you the higher multiplications on the modules. The pairing theorem ends up being a consequence of a topological fact, which is that this finite set of parameterized handle bodies is enough to resolve any ordered three manifold into, if you like, a hypercube of three manifolds in the sense of the branch double cover, I might say, spectral sequence that Peter talked about. Analogously, in the sense that Kavanagh can resolve any link into a complete resolution into circles. You can resolve any ordered three manifold into some kind of resolution cube of simpler objects. These parameterized handle bodies pass with connect some dimensional parts of twos inside. This allows you to reduce mean, proving that sort of module version of the circular triangle allows you to reduce the pairing theorem to the case where the two things you're gluing are actual handle bodies. And in that case, the proof looks kind of deceptively simple. The point is that the complex, the module we associate to an actual handle body can be identified as the image of the algebra under an idempotent that's actually associated to that handle body, it turns out. So, in other words, there's an idempotent in this algebra which kills all the other summands and just gives you this summand when you apply it. And so, if we're looking at the A-infinity tensor product of these guys, we can rewrite that as A sigma I alpha tensor A sigma I beta. Move around some parentheses. The A-infinity tensor product of the algebra with itself over the algebra is the algebra, as it turns out. And by definition, this gives you the alpha beta summand of the algebra in the end. So, what is the alpha beta summand of the algebra? It's nothing but the complex that you get. Including H alpha to H beta. Okay, I'll stop there.
Other questions?
Yeah.
What is the instruction of doing exactly the same thing with the first?
So, in a sense, this exists for the fluid homology. Well, this A-infinity category exists in the sense that, but where your objects are, say, all handle bodies, or if you think of them as all alpha, sets of alpha curves, right? Those are your objects, and given the sequence alpha, beta, gamma, delta, whatever, you get some polygon maps, and these give you an A-infinity structure. There isn't such an obstruction to doing it, but this way. But now the proofs that we have don't translate immediately to the way things are done in negative for homology. I should just say that. There isn't much obstruction. But what we're doing is really a topological thing with 3 manifolds and 4 manifolds. This translates immediately to instant time, for example, provided that your instant time groups are well defined, which nowadays, in many cases, you can do by tricks of, Peter and Tom and others. Much of it translates to negative.
So, second question. Does this reduce, if you do the same thing with your homology, does this reduce the problem proving that the two things are isomorphic to a check of finitely many examples?
Checking out.
Computing finitely many.
No, so essentially, all right. So it's a good question. In a sense, what we're saying here is that the Floer homology of this manifold with boundary can be completely understood. Of any 3 manifold with boundary can be understood by just looking at these. The whole theory is determined by just looking at these parameterized handle bodies, just those guys. But the catch is, it's not simply the Floer complex you get by gluing those together. It's also all of these maps, all of these higher maps as well. In other words, all of Floer theory, let's say we're in the closed 3 manifold case, right? an easier topological theorem than the one we're proving with this boundary case is that any three-manifold can be resolved through surgery triangles into a hypercube of S1 connect sums of S1 cross S2. So any three-manifold is quasi-isomorphic to a complex, which is a direct sum of complexes which themselves are Floer complexes of S1 cross S2s, whose generators we can tell you exactly what combinatorially, these are the generators, there's some exterior algebras. The problem is that to define the differential, you have to consider not just each of these vertices of this hypercube, the internal Floer differentials, but also the chain maps, the base maps, the higher maps. So you could say Floer homology reduces to understanding S1 cross S2s, but you'd be lying because you also have to understand the maps induced by these sort of multiple coordisms between S1 cross S2s, connect sums of them, but not just those with families of metrics, certain families of metrics. Or on the Hagar-Floer side, you have to understand polygon maps between them. It's not clear if you're just pushing around the difficulty or if you're, but it does feel like you're axiomatizing somehow.
More questions?
Can you say something quick about why this is actually easiest for HM as to any of the other versions?
Yeah. Okay, so I mentioned that the reducibles are an issue in multiple Floer, Dixon-Tom Floer, and so on. This isn't why you get three different theories. So the reducibles, they refer to the fact that this configuration space should be Morse theory on has a boundary. Steven mentioned, because the gauge group doesn't act freely, they do some blow up, and then they push it. The blow up introduces boundary. And so, if you like, you can think of these versions from, let's see, bar, to, and from as analogous to the homology. If you have a manifold boundary, you talk about the homology of its boundary, the absolute homology, or you can talk about the relative homology. And in a sense, that's what these three versions are. They're, a Morse function on a manifold boundary, this infinite dimensional configuration space of boundary, and it gives rise to three theories depending on what you think of the boundary, the absolute, and the relative. When you start to define the chain maps and these maps with families of metrics for coordisms with more than not just one incoming and one outgoing n, you run into trouble because of these reducibles. And what I can show is that in the case of, in these cases, there is a chain map whenever you have exactly one outgoing n. You can have arbitrarily many incoming n's. As long as you have one outgoing end, it's possible to write down some operator which counts all kinds of reducible, irreducible trajectories, concatenations of them, but does satisfy the relations you want. Even in this case, there's like 17 terms to define this operator. And then the relation that it's a chain map has hundreds of terms, counting different kinds of concatenations of trajectories between different types of critical points. In this theory, it's somehow dual. So here, you get maps as long as you have one incoming end, but you can have as many outgoing ends as you want. And so, when I say all versions, what I mean is the thing that's easiest, well, either of these, because naturally I can talk about ends, as many ends as I want coming in, and then ends going out, and that's what the A infinity structure sees. Or I can do this with boundaries, I cut it into such pieces. In this case, everything is sort of turned around. So I don't know what the right formalism is. It's probably co-algebras and OA infinity algebras, whatever this means. I haven't thought much about it, but that's why I can see these versions. And then you said, why not the HAT version, maybe?
Why not the BGA?
What?
Why not the BGA? Why not the BGA?
Why not the BGA? What do you mean?
The formalism you get in the case where you have one input and many output.
One input and many output. The type D stuff that. So that's why you didn't see me talk about type D structures. I'm only talking about the infinity algebra modules and tensor.
No, exactly. You don't know what kind of algebra you get in that equation.
Oh, what I mean is, I assume there's a dual notion that flips everything the other direction. no higher.
No, I mean, they are all, instead of having, should look at lighting and I don't know, the contact, the joint contact model.
Okay, yeah, let's talk about that. So anyway, there's this duality, and you know, somehow deep down it has to do with the fact that the maps we associate with cobordism, you know, what we're doing is, you should think of, you have sort of the subgrid monopoles on the cobordism, and you have the configuration space, we call this N1 and 2, you have sort of, the configuration space of the disjoint union is something like the product of the configuration spaces. And so, if each of the configuration spaces has boundary, then the product now has corners, and suddenly, when you want to do pull-up, push-down, you run into trouble because you have to use concrete duality to do, you know, you should think about this as a correspondence, a pull-up, push-down. You want to make sure that wherever you're going to dualize in 2 places out of the 3, up here and one of these, you want to make sure that you're not dualizing where there's corners. So that's why, you know, if you think of these theories as one being kind of like homology, one like cohomology, that ends up switching where you have to dualize. Anyway, philosophically, this is somehow why there's problems going, I mean, the other way in each of these theories. Maybe they'd be solved if there was some deeper notions of dealing with corners, not just boundary and so on.
Okay, let's say Jonathan.